Now another type of isomer, that is optical isomer. Optical isomer also can shown by the complexes like geometrical isomer. This optical isomer is very simple. Uh, Let us consider one example. I will take this example to draw the optical isomers. Every complex cannot show geometrical isomer. Every complex cannot show your optical isomer. So what type of what type of complexes can show geometrical isomer? What type of complexes can show your optical isomer? Only that type of complexes I have shown here. All type of complexes cannot show. So now this is one of the complex. You can draw the complex like this way. Since the coordination number is 6, ethylene diamine is bidentate ligand. So you can draw the complex like this way by doing octahedral shape. One en is here, another en is here, one chlorine is here, another chlorine will be here. Already you have drawn cis and trans. This is cis or trans. These two are in opposite position, na? That's why this is trans isomer. Now I will draw another one for this complex. Cobalt, six bonds. Suppose one chlorine is present here, another chlorine is present here, one en is here, another en will be here. This is said to be the cis isomer because these two positions contain similar ligand. That's why cis. This is trans, this is cis according to geometrical isomer concept. To draw the optical isomer, what you have to do? You take one mirror. Suppose this is one mirror, this is another mirror. So you have to take one mirror. After taking mirror, you see the mirror image. In this case of this is cis isomer. If you draw the mirror image of this complex, then it will be like this, cobalt, and the 6 bonds are like this. If you draw the mirror image, then one chlorine will be here, another chlorine will be here. Ethylene diamine, one goes this side, one goes this side. But if you take the mirror image of this one, I think it will remain same. There will be no difference between the object and the mirror image. One en will be here, another en will be here, one chlorine will be here, one chlorine will be here. Now let's say when you take the mirror and you look the mirror image, if the mirror image is completely similar with the complex, that type of complexes cannot show optical isomer. But if the mirror image is something different from the original complex, here this en is on the right side, now it goes to left side, so some different in their position you have got. That's why this complex can show optical isomer. So that is why when you draw optical isomer of some complexes, you consider one mirror and you look the mirror image. If the mirror image is exactly same, that type of complex cannot show optical isomer. So trans isomer, actually this is trans isomer. Trans isomer cannot show mirror image. I mean trans isomer cannot show optical isomer, but cis isomer can show optical isomer like this way. So this is about the optical isomer. If you want to draw optical isomer of any complex, then you see the mirror image. If the mirror image is something different from the original complex, that means it can show optical isomer. And if the mirror image is exactly same with the original complex, that means it cannot show optical isomer. Now one theory which is called Warner coordination theory. Warner coordination theory. Warner is the name of scientist and he discovered this complex compound, and for discovering this complex compounds he got the Nobel Prize also. So Warner put out a theory for the coordination compounds that is called Warner's coordination theory. Now what are the main points? The main points are, I will give you the points. Suppose this is one of the complex. In every complexes, the metal atom exhibit two types of valency. One is called primary valency and one is called secondary valency. Actually, what is valency? Valency means, suppose a metal aluminium, it contains 3 plus charge. I mean the valency of aluminium will be 3. So what charge contained by the element, that is called valency. Another concept of valency, an atom contain how many number of bonds inside it, that is also called a valency. So here, if you want to find out the charge of cobalt, cobalt is X, water is neutral 0, chlorine is -1 into 2, but bahar mein kya hai +1, this is equal +1, so X is equal what, +3. That means here the cobalt oxidation number is +3. I mean the primary valency of cobalt is 3. So what is the oxidation number of the metal? What is the oxidation number of the metal in the complex? That oxidation number represent primary valency. And how many bonds present with the metal? Since there are 4 water, 2 chlorine, total number of bonds you will get 6. Number of bonds also represent one valency, na? So here the secondary valency will be 6. So in every complexes, the central metal atom exhibit 2 types of valency. One is primary valency and one is secondary valency. Primary valency means nothing, the oxidation number of the metal, and secondary valency means nothing, the coordination number. I mean how many bonds present with the metal. So this is the first point of Warner coordination theory. In every complexes, metal exhibit 2 types of valency. One is called primary valency, I mean oxidation number of the metal, and one is called secondary valency, that is the coordination number of the metal. The second point, primary valencies are satisfied by only negative ligands. Primary valency do not satisfied by the neutral ligands, but secondary valency satisfied by both neutral and neutral and anionic ligands. What is the meaning of this? When I determine primary valency, there is no contribution of water. The contribution given by only chlorine, because water is neutral 0. So when you determine the primary valency is not satisfied by the neutral ligand. It is satisfied only by negative ligands. That is one point. But secondary valency, when you determine, how you determine the secondary valency 6? Here 4 water, so 4 bonds will produce, 2 chlorine, another 2 bonds will produce, total number of bonds will be 6. I mean, when you determine the secondary valency is satisfied by both neutral and anionic ligand. And when a complex maintain the secondary valency, I mean when the ligand comes towards the metal, they always comes with a direction. Suppose this is cobalt, all the 6 bonds cannot form like this way. All the 6 bonds cannot come like this way. When they comes towards the metal, they always come with a direction, and that is why you will get a definite geometry of the complex, and that is why when coordination number is 6, you will get the octahedral shape, because the ligand comes always with a direction. And that is why to maintain the coordination number, when you draw one complex, you should maintain the coordination number, you should maintain the primary valency, and you have to maintain its geometry also. I mean whether it contain square planar shape or whether it contain octahedral shape, like that. So these are the main points of Warner's coordination theory. Thank you.